Hi, my name's Jacob, uh, and with
Name's
me is Connor Mooney.
right here.
Mhm. So we'll be delivering a presentation on our research into optimal two-qubit quantum circuit synthesis. And so involved in our team, of course, the principal investigator, you just heard her, Dr. Mingjin Tian of the GMU Physics Department. We have two co-PIs as well, Dr. Andrew Glaudel of Booz Allen and GMU Math, as well as Dr. Michael Jarrett Bohm of Booz Allen and GMU Math as well. And we have three undergraduate students. We have Ian Morris, and you'll hear him present on Qiskit later. And of course, you have Connor Mooney and myself. So first, we thought it would be helpful to give some more background on quantum computing. And so as you've heard before, quantum computers, they're very similar to classical computers, at least in most sense. But the primary difference is that they use quantum bits or so-called qubits instead of classical bits. And so the primary distinction is that these qubits can utilize certain quantum properties, such as superposition, where instead of existing in a state of only 0 or 1, as a normal bit does, they can exist in a combination of these states that can be useful for performing certain computations. And additionally, they can also be entangled with one another as well. And so these properties it's been proven that they can solve certain computations much faster than any classical computer could. So another point that we want to make that can lead to some confusion is that the use for quantum computers is a bit more specialized in the sense that they won't be replacing classical computers for everyday purposes. Like, we won't all be using quantum laptops 10 years from now. Instead, it's more like they will be used for certain specialized purposes. So something like, how we have a central processing unit, a CPU, a GPU. In the future, there might be a QPU, a quantum processing unit, that we can use for certain computations that are much more expedient to be done with qubits. And another point that I think I'd like to stress is that the fundamental toolkit for sort of understanding quantum computing is linear algebra. And so a lot of this might seem a bit, quantum computing all seems a bit, high level, but really even from an undergraduate level, if you have the basic tools of linear algebra, the bar to entry into this field is not too high. So I think a lot of undergraduates that might be intimidated should see that if you have a basic understanding of this linear algebra, then you can enter the field without too much difficulty. So another thing we wanted to talk about is how there have been a lot of recent advancements in the field of quantum computing, because it's a very quickly growing field. So for example, the Sycamore processor that was built by Google, it managed to establish an example of quantum supremacy, where it performed a calculation in 200 seconds that for even the fastest classical supercomputers would have taken somewhere in the realm of 10,000 years or so. And so this is sort of a clear example of how quantum computers can provide a very tangible advantage over classical computers. And it isn't just Google as well. There are a lot of other companies like IBM, and more close to us geographically, there's IonQ, which is based out of Maryland, that are pretty close behind in terms of developing quantum computers with a large number of qubits. So, and there are also, of course, advantages in other parts of the world. So in China, there was recently, they managed to complete building a communication network that spans about 4,600 kilometers that's capable of quantum communications on a massive scale we haven't really seen before. And also, there's a lot of research being done as well into the field of post-quantum cryptography as well, sort of as a response to, these new advancements in quantum computing. So before we dive too much into the weeds of quantum computing, it helps to sort of establish some of the basics of classical computing. Because in classical computing, you can model computation in a sort of circuit design where it's composed of logic gates acting on these bits, right? It can be 0 or 1. And so this is a very useful way of understanding computations because, for example, if you have this AND gate, right, that I'm sure most of you are familiar with, if you take 2 bits as an input, then you can output the product of the 2 input bits, right? So if, both of them are 1, then you get a 1. But if one or both of them is a 0, then you get a 0 as the output. And so these very simple gate designs, they can actually provide a very sort of, complex circuit diagram to, produce these desired computation that you need. And so it's useful to have an analogy here for quantum circuits, which we are concerned with, of course, that are similar to the sort of principles of classical circuits. So now we'll touch on quantum gates. So quantum gates are sort of similar to classical gates, they're the building blocks of these quantum circuits, right? And so these gates generally act on 1 or more qubits to perform certain operations, right? And in particular with single qubit operators, we can sort of imagine the function of an operator as being sort of a rotation of this 3-dimensional sphere, which we call the block sphere. So you can see an example on the left of this block sphere where, we have the 2 sort of cardinal directions, the 0 and 1, that a normal, bit can exist in. But we can also perform manipulations of this qubit state to end up in a variety of different sort of superpositions that are located on this block sphere. And so we can perform then calculations by combining rotations of this on this sphere. And most circuits are also built using combinations of gates that act on 1 or 2 qubits, because creating gates that involve more qubits at once tends to be a sort of intractable problem. But another thing that's important to realize about this is that in general, quantum mechanics are reversible. And so what this means for when we're defining quantum gates is that these gates need to be defined in a way that is then reversible as well. And so we encode these gates by defining them as unitary matrices. And so these unitaries, they map rotations around the block sphere. So you can sort of view it as, you can, for example, the X gate functions similarly to the classical NOT gate, right, where we rotate from the 0 to the 1. And there are a wide variety of different single qubit operators that function like this. And the main thing to note here is that they're always reversible, because if you rotate in one direction, along this sphere, you can always rotate around again to get back to where you started. And so these matrices then, in a more physical, tangible form, they represent quantum mechanical operations, just abstracted.
Okay, so we have
take the floor.
Yeah, so we have quantum gates that correspond to classical gates. So it would seem to be fairly clear that we would also have quantum circuits that correspond to classical circuits. And once you abstract it essentially up to the circuit and gate level, they look almost the same. The only difference is obviously instead of and or not gates, for example, you have other quantum gates. And which gates we're using in this case are actually, there's specific sets called universal gate sets. And what they can do is any general unitary, so rotation on the space of multiple qubits, can be approximated arbitrarily well by a universal gate set. It's a little different from classical because you can't outright generate any operation, but you can approximate it. And so that's one of the few small nuances between a classical circuit and a quantum circuit. There's just a little bit of different mathematics under the hood. And gates essentially naively correspond to certain operations. There's something called an X gate, and the X gate is very similar to a NOT gate. It just works on qubits as opposed to classical bits, for example. And below you can see an instance of a quantum circuit where you see the wires that are going horizontally correspond to qubits. The boxes are single qubit gates, and then the vertical wires correspond to 2 qubit gates. So you have on the top qubit, it's being operated on by an S gate. Then later it's operated on by I think a C0 gate, and then a Hadamard gate, or an H gate and a T gate, and so on and so forth. And these gates are actually something called the Clifford plus T gate set, which we will talk about on the next slide. So first thing we need to do when we're talking about circuit synthesis is we need to choose a universal gate set to work with. And it turns out there's a gate set called the Clifford plus T gate. So that's the Clifford gates, which are just kind of very easy to implement. On the slide, it says inherently quantum. And those are just super nice, super easy. And then there's the T gate, which is not so nice, but it's necessary because without the Clifford gate, without the T gate, Clifford gates aren't universal. So that's just a necessity in order to make it into a universal gate set. And so why do we want to use the Clifford plus T gate? So overall, Clifford qubits are delicate. It's there's this whole problem of decoherence, for example, where if you perturb the system even a little bit, qubits will just essentially break down. You'll lose all the quantum effects. So you need protocols. You need ways of implementing the hardware that are very resilient to that can actually mitigate that error, detect that error, and so on and so forth. And it turns out one of the things Clifford plus T gates are good at is doing that. They're very useful. If I remember correctly, I think they're called fault tolerant quantum gates. And then among other things, that's just one of the few things. They're also what is called a super golden gate set, which essentially just means it's a very, very good set for just building things in general. It's just convenient. It's a little too technical to describe why that is. And then essentially because of that, they've also been starting to be used like in the future forward-looking quantum like research. So in other words, it's just good to know how to work with these and make them essentially just know how to make circuits out of them, right? So it's just, we've almost set it up that way. And so what exactly are we doing in our research? Jacob, if you could go to the next slide. So our goal is to do something called circuit synthesis, which is, and make it optimal. So what that means is we want to have a circuit and we want to make sure that we can reduce it to the least amount of T gates as possible. So on the right, you see an image of a Rube Goldberg machine, which we'll be using as an analogy for our quantum circuit. Notice how all it does is staple paper. So that means, right, you could remove every step except for I, and you'd have essentially the same operation. So in other words, you can simplify that circuit like prodigiously, and you'll still have the same operation in the end. And so that kind of idea is what we're doing. But instead of these different steps of like an alarm clock and all the stuff that's going on in there, you have T gates, which are essentially the metric we use to judge complexity. And this has been solved for 1 qubit, but not 2. And essentially the reason is the problem gets quickly significantly more difficult as soon as you start adding more qubits. And essentially the idea was that we have fundamental relations between gates, and we try to simplify the circuits using that. So for 2 qubit, the relations are kind of more complex and it gets much harder. And for 3, it's even more hard, sorry. And so essentially that's kind of the idea. And I'll talk a little bit more about the complex relations on the next slide. So the idea of relations between gates is fairly intuitive. Think of like how 2 NOT gates cancel each other out and they essentially act as the identity, right? So that means if you see 3 NOT gates or any odd number of NOT gates together, you can just replace that with 1 NOT gate. And the circuit has gotten significantly simpler. Similarly, if you have an even number, you can just take them all out. And Clifford plus T gates have their own relations, which change a little bit based on the number of qubits. So some instances of the relations are right below there. So you can see some of them are really complicated and some of them are a little bit more workable. The one on the bottom is just saying that up to a phase, 2 circuits are the same, which is pretty workable. The one on the top, not so much. But the idea is that if you can, those patterns were what was used to analyze them in the 1 qubit case. And we're trying to do something somewhat similar to that. So our research, the first thing we do is we take the 2 qubits and we are going to shift them using something called an isomorphism into a space that we can actually more easily understand. So the graphic on the right is showing the instance of a graph isomorphism. So you'll see the 2 concentric squares, or not necessarily concentric, I don't know how to describe it. And then they are being converted into a bipartite graph. So the idea is these are the same graph, they're just looked at in a slightly different way, right? And so that's the same idea with isomorphisms everywhere else. If you've seen them in algebra, you might have seen them in linear algebra, you've seen them in a lot of places. But anyhow, the idea is that they're the same object, they're just looked at in a slightly different way. And the way we're looking at it is we are essentially taking 2 qubits and 2 qubit operators, and we're looking at them as rotations on the 60 6-dimensional sphere. So similar to the blocks here, a little harder to visualize, but the same idea. And essentially what we're trying to do is look for patterns in those rotations, look for patterns in that isomorphic space. And that is the basis of how we're going to analyze our circuit construction. So currently, what we're doing is we're looking at these higher dimensional analogs of the operators, and we're trying to find the patterns that we've exploited. We've written a code base to start dealing with that, and we've started cataloging a finite set of patterns that we're caring about. Essentially, because there's an infinite set of these operators, but there's only a few characteristics that we actually, compared to infinity, there are significantly less characteristics we actually care about. It's like if you take the integers and you can look at them as even or odd, for example. And then based on these patterns, we're trying to find relations between these different classes of patterns and using them to simplify the thing, saying, oh, this is related to this pattern by this, so we can pull this out. It's a little vague, in this talk, but we're just using those patterns as kind of heuristics to find a way we can make sure that it's an optimal T count. And yeah, so that's our talk. So thank you for your attention. And if you're curious or want to learn more and want to get involved, contact Dr. Tian. And here are some photos of our collaborators. I think all of them are actually here, but yeah, thank you very much.
Thank you, Jacob and Connor. Great talk.
Thank you.
The questions you can put in chat or just unmute yourself and ask. On Gather Town, we also have the room number 3 for the discussion of the questions related to this quantum computing research. So if I want to move over there, that's fine too.
Hi, can I ask a question?
Please.
Yes. My name is Dr. Jason Lee, and back in 2009, I was actually working with Ming on simulating single qubits. This was around the time that I guess the field was really starting. And even though I dropped out of the research, I was a grad student at Mason at the time, and I didn't go back into this until recently because I'm seeing the technology has really developed since 2009. And as for you guys, for the ones that just did your presentations, I actually have to say thank you because you really cleared up a few things, the concepts I've been trying to catch up on that I hadn't had time to catch up on, like how a quantum computer versus a single computer, how the different classical computer, I should say, how the differences are very different. Like it's not something we can actually combine together. My question regarding what you've just talked about is how realistic is it to build a quantum computer ourselves, like a single qubit system?
I'm not too well versed on the hardware side. I think currently it's probably a little unfeasible, obviously it depends on how many resources you have. But as a hobbyist, I feel like it would probably be, this is mostly speculation. So if anyone wants to hop in with more knowledge, they can. But I think it would be fairly unfeasible. Not to say that people can't do it. I mean, people have built nuclear reactors in their backyards before, but
yeah,
I'm not sure.
Back in 2009, when I was getting into this, I really was more interested in how we would build one, how to build a quantum computer, how it would translate to a quantum processor, how we would get to something working as what we would understand as classical computation. So as I understand now, there's a huge difference, but I have always been more interested in understanding how would we build one. And it sounds like the bigger ones, they're not much different than a 2-qubit system. They don't even go as high as past 10 qubits, at least the working feasible models that I understand. Physical.
Well, I think there have been quantum computers built with upwards of around 50 qubits or so concurrently. But also it helps with the fact that I think, as Ian's going to talk about later with Qiskit, we can actually run these quantum circuits, even if we don't have our own quantum computers available to us at Mason. We can run them online using the IBM that, and we can, run these programs remotely, which makes it a lot easier by giving us access to this directly.
All right, thank you very much.